Czy widać wszystko?
Kamera padła.
Widać wszystko.
Jak to wpadło do ejektorów? Do sesji z ejektorami. Powinniśmy chyba zaczynać.
So Matusz will provide us information. We have 1 minute. Okay, so I guess that maybe we can start the session. Good morning to ladies and gentlemen and colleagues. This is the second session which will be focused on ejectors, but in fact this session covers the presentations also on heat transfer equipment, heat transfer processes, ejectors, injectors. And the first paper will be presented by Adam Łapiński from Białystok University of Technology, and will be dealing with experimental investigations of heat transfer in packet bed of vegetables and fruits. Okay, Adam, you can start your presentation.
Okay.
12 minutes.
Good afternoon. My name is Adam Łapiński. I'm a worker in Białystok University of Technology, and today I'd like to present the experimental investigation of heat transfer in packet bed of vegetables and fruits. My presentation consists of the five sections. First, introduction. Next, I want to present the methodology, single blow technique, and the model of heat transfer. Next, I will present the testing stand, results, and the last. My presentation consists of the 30 slides. The knowledge on the heat transfer condition during cooling of vegetable and fruits is very important when we want to design of the storage chamber. The paper presents an approach for the measurement of heat transfer in packet bed for the exemplary case of carrots in two various arrangements, and packet bed of, for example, apples. The beds, vegetables and apples is the in this paper consists of the elements of the complicated geometry, which means that the use of the heat transfer correlation on the simple geometry may lead to not acceptable prediction accuracy. From my experience, I use method of single blow technique. The measurements in the single blow is to record the time variable of gas profile direct at the inlet and outlet of the tested packet bed, which caused by switching the heating section on or off. But when we use this method, we must need two following conditions. First, the gas flow is steady state, constant velocity. The second condition, the temperature is in the measurement section is constant and equal the axial and radial direction. But this method have one problem, because we must realization. This is very difficult, and we must realization of the immediately temperature jump the bed inlet. But when we use right model, this problem is not very important. There are many models for the determine the heat transfer coefficient, but the most effective model for me is the model Yang and Yang. The author proposed the dimensionless inlet temperature profile obtained in the discussed test method after switching the heater on and off. After applying appropriate initial and boundary condition, the authors obtained a solution in the form of two equations. First solution, when the temperature jump did not reach the tested bed outlet, and second solution when the temperature jump did reach the tested bed. And for me and I use for the second solution. Okay, this is schematic on my test extent. They consist of the 4 sections. First section, the install flow straightener and additional, I measure this section measure temperature on the inlet tunnel and flow velocity. Next section is the change the geometry tunnel. First section is the measurement section. I measure temperature inlet and outlet bed, difference pressure, humidity, and intensivity of turbulence. And the last section 4, where the installer install the fan. In my experiment, I have checked what happened in the heat transfer coefficient when I change the intensivity of turbulence. And to measure intensivity of turbulence, I use the Dante Dynamics probe, Streamline Pro anemometer. And when I change the intensity of turbulence, I have the put on the first section box, feature 4. When the first section is empty, intensity of turbulence equal 2%. But when I put on one boxes, intensivity of turbulence equal 7%, but two boxes is to 14%. This is my packet bed testing. I have test two arrangement packet bed of carrots, irregular and longitudinal, and one tested packet bed of apple. On the table, you see the parameter on this packet bed: average mass, heat transfer surface area, average volume, and density. Validation. First, in my experiment, I prepared validation single ball method. As you can see, my tested bed consists of the ball. My results, I compare the correlation developed by Alvarez and Flick for spherical elements. And figure 6, you can see a comparison of my results of packet bed and correlation of Alvarez and Flick. And as you can see, this is very It's very similar results. The measuring range number Reynolds 2,000 to 3.5 thousand. Results of my experiments. As you can see, 3 graphs. First graph, this is the results of carrots arrangement longitudinal. Second, carrot arrangement irregular, and the last graph, this is the and as you can see, this graph, the intensity of turbulence from 2 to 14% doesn't not affect the intensity of heat transfer inside the study bed, carrots and apple. Next graph, I compare the arrangement for the carrot bed, and as you can see, the different turbulence, the influence of carrots arrangement on the intensity of heat transfer is very visible, and the number of Nusselt is higher when we tested of the packet bed carrot in irregular. On the basis of the obtained results, criterion dependence were prepared for the Nusselt number as function, number of Reynolds, Prandtl number, and intensity of turbulence. And 4 is the correlation for the carrots. Correlation the carrots with longitudinal arrangement. 5 is the correlation the carrots with irregular arrangement, and 6 the correlation for the apple bed. Conclusion. The comparison of heat transfer results for various tested bed arrangements and at various intensities of turbulence allow to analyze the influence of these parameters on the transfer. In all tested cases of the tested packet beds, the turbulence intensity does not produce a significant effect on Nusselt number describing heat transfer. This may be attributed to laminarization of the airflow. Inside the bed, the range of Reynolds numbers on the inlet to the bed was from 1,300 to 11,000, which indicates a transitional and turbulent flow, while the range of Reynolds number inside the bed were number Reynolds equal to from 200 to 1,700. The influence of the bed arrangement on heat transfer is significant. The results show exchange heat transfer for the case of the irregular arrangement carrot bed. This is the reason for the separated heat transfer correlation that were proposed for these 2 cases of the carrot packet bed.
Okay, thank you very much
for attention.
Thank you very much for your presentation.
And do we have any questions for this presentation?
There is no questions on Slido. I didn't see it. No questions.
So maybe if we don't have questions, and the situation is very unique just because the presentations are consistent with the same research group, in fact, so that maybe we can just go to the next presentation. And the next presentation will be dealing with numerical design and operation of the ejection refrigeration system driven by low-grade heat. And this is a presentation combined of the research group from the Białystok University of Technology and company Marani from Zabrze, Poland. And presenter will be Professor Kamil Śmierciew. Okay, so you can just prepare your presentation.
Thank you very much for introduction. So I will start my presentation. Ladies and gentlemen.
Maybe I really don't know whether we should start precisely at 3:15, just because there are 4 usual sessions. So in order to have the consistency with the other.
Okay.
Okay. So maybe we have maybe 1 minute for preparing or maybe discussion if you anyone can just ask any questions. Okay, so I guess it's 1:15. Yeah, you can just start your presentation.
Okay, so I will start. Thank you for introduction. So today I will tell you something about numerical design and operation of the ejector system. The system is driven by waste heat and is dedicated to the air conditioning purposes. And this is a more engineering approach than science in my presentation. I have a typical content, so I will start. Our job in this project was to design, then manufacture, and eventually testing and develop and implemented the ejectors for the air conditioning system. As I said, the system will be driven by waste heat. The heat will be taken from the air compression systems, and we are dealing with, as you can see on the tables, we are dealing with 2 sets of operating parameters. The first, we have 200 kilowatts of thermal capacity. This is the motive heat. And the second one is 600 kilowatts of motive heat. For the first case, we are aiming in 35 kilowatts of cold. And for the second case, we are aiming for 125 kilowatts of cold. And we have 2 sets of operating temperatures. I mean the motive temperatures. The first one is 80 centigrades and the second one is 150 centigrades. So for the second case, we are dealing with supercritical cycle, and for that reason, we just assumed that we will operating with 3 megapascals because it's above the supercritical or above critical point. And for the first case, we have saturating conditions. The evaporating temperatures are set as 3 centigrades, slightly superheated vapor, and we are trying to obtain the typical cold water condition 6-12 centigrades. And we have tested 2 refrigerants. The names or it was the refrigerant 12330ZDE and 1336MZZZ. So for the case of designing the ejector, we used Huang approach. We slightly modified this model. For example, we did not use the perfect gas assumptions. We are dealing with real gas thermodynamic properties, and we slightly modified the part of the model where the geometry of mixing chamber is calculated. So once we obtain the results for all of these cases, as we can see, we designed 8 ejectors for 2 refrigerants. It turns out that the ejector dedicated for the first refrigerant has a slightly smaller dimensions than the ejector designed for 1336. So we choose the first one. The table shows the diameters or dimensions in the dimensionless form, so I cannot show you the direct numbers. It is presented in the dimensionless form. So once we calculate this ejector, we found a very interesting thing. It is related with the isentropic efficiencies of the ejector components. As you can see, these are more or less typical cited in the open literature efficiencies of the components of the ejector. But when we take the multiply these efficiencies, we get the so-called parameter K. And if the K, for example, we have a 1, 0.79 and 0.68. So as you can see, these efficiencies result in different performance lines. So it is very important to know what kind of numbers we should assume in order to obtain the best possible solutions. Of course, it is important, especially for the designing. As you can see on the right hand side of the on this figure, we have experimentally tested these parameters. As you can see, first of all, they are not constant, and they can have a different value for the different operating parameters. So the engineers should remember that the results are depending on the assumed efficiencies. So the next step was related with CFD. So we built the 3D model. We put some mesh on the model. This is the photo of the surface mesh. This is the volume mesh. Some statistic, the average value of the mesh quality it's very promising, because we are here, somewhere here. So the mesh was very good in quality. We perform mesh independent tests. So we have calculated 500,000 and 250,000 of cells. We have tested mass flow rates for both streams, so the primary streams and the secondary stream. The results are given here. And this part of the graph is the end part of this calculating of these calculations. Next, we compared our results in terms of, we compare the perfect gas and real gas. So for this comparison, the difference is just below 2%. And if we compare 0D model and 3D model, both are for the real gas, we can see that the difference is 11.40%. So this is the table where the results are collected together. So maybe I will skip it. And this is the streamlines for the exemplary point. So as you can see, we obtained a typical flow inside the ejectors. These are a huge, you can see there is a big vortex in the diffuser. This is the location of shock wave here. So the path lines were just like we expected. When we have tested the geometry that we obtain from 0D model, we focus on the modeling on the performance lines for the design and ejector. So for this case, for this purpose, we used a model developed by Chen in 2013. It was also slightly modified, especially in terms of calculation of shock wave. We used an approach where the shock wave is calculated using the intersection of the energy and the momentum equations. These are the Fano lines and the Rayleigh lines. So this is the theoretical graph, and this is the results of numerical simulation. So the performance lines of the tested ejector are presented here. So we compare the 3D model with the 0D model. As you can see, they are quite a difference, especially in terms of the critical point where the flow is transformed from the on design operating regime to the off design. It means that the secondary flow is not choked here in this region, and the critical temperature is different for the 3D CFD model and 0D model. So the difference is like 2 centigrades. However, as I said, we aimed at 35 kilowatts. It turns out that we are able to obtain a slightly higher value than 35. So it was our intention to improve the ejector operation. So we try to modify slightly this geometry, and as an expected effect, we should get a higher critical temperature for this performance line. So, as you can see, the basics for the modification of the geometry was location of the shock wave. As you can see previously on the path lines, the shock wave is located in the mid part of the mixing chamber. Usually we are trying to design the ejector in such a way that the shock wave is located at the end of the mixing chamber. So for our case, we were able to reduce the length of this mixing chamber, and we slightly modified the suction chamber in order to reduce the potential vortices that may occur inside this suction chamber. So we did some changes in geometry, and finally we obtained the results as given here on this figure. So we once again, we compare the basic geometry obtained from 0D model, and after small modification, as you can see, the motif nozzle does not change. However, the changes were the changes made are for the mixing chamber, and of course we have to slightly modify the diffuser in terms of to have smooth connection between mixing chamber and the diffuser. So as you can see, the cooling capacity is slightly below 35 kilowatts. However, it is accepted for us, but we've got what we want to get. So the temperature of the critical temperature when the secondary flow is not choked is high, is quite is a bit higher than the previous one. So our modified geometry was was the final geometry. So to conclusion, we used the lumped parameter model for the designing part. Then we made some performance. We made some calculation in order to have a performance line. We used a CFD. We compared the CFD with 0D model. The results are very in very good agreement. We are able to slightly modify the geometry of the ejector, and we obtained a higher temperature that that is critical for the best operation of the ejector, because if the temperature of transformation from on design region to off design region, we want to get the highest possible temperature for this transition. Okay, so thank you very much for your time, for listening.
Thank you very much. You have finished sharply at the very end of this presentation, so we don't have time for any questions.
Oh.
So after presentation,
Are there any questions on
no,
the
I don't see any questions
on Slido? Okay.
System. And before we can go to the next presentation, and in the next presentation we'll be dealing with also a kind of compression devices. So it will be just ejector refrigeration cycle, but the issues of the application of zeotropic mixtures as the working fluids. And this presentation also was prepared by the research group from Ballistic University of Technology, and the presenter will be Paweł Jakonczuk. So could you just prepare your presentation, Paweł? Okay, so you can just start the presentation just now.
Oh, I'm sorry, I didn't unmute. So I will present a thermodynamic analysis of an ejector cycle, but with zeotropic mixtures as a working fluid. The ejector cycles require a large flow of heat source fluid due to the low drop in source fluid temperature, because most of the heat is transferred to the cycle during a phase change. And better utilization of a heat source temperature, so achieving a higher drop in heat source temperature, could potentially broaden application possibilities for ejector cycles, for example, using district heating as heat source. And desirable heating fluid temperature drop would be around 20 to 30 degrees. So these are the requirements we've set for this analysis for the working fluid. So the critical point should be low to further lower the amount of heat transferred during the phase change. The COP, of course, the refrigerants should provide a high COP. It should be dry or isentropic and easily available. GWP should be below 150 to stay compliant with the EU regulation number 517. And the refrigerants should belong to A1 or A2L safety class. So the better matching of the cycle and heat source can be achieved by using supercritical, transcritical ejector cycle, or by using zeotropic fluids. And due to the lack of environmentally friendly refrigerants with properties which would be suitable for transcritical operation and low temperature sources, only zeotropic cycle was analyzed, and the analysis was performed using new blends. And at the end, the comparison of zeotropic cycle pump power consumption and compressor power consumption of an equivalent vapor compression cycle was performed. And by equivalent compression cycle, I mean a cycle that would work within the same temperatures of evaporation and condensation, and yielding the same cooling capacity. And if significant mechanical power consumption savings could be possible to achieve with zeotropic cycle, this would mean that this solution could be economically competitive if a suitable waste heat source is available. So in the table, we can see the blends used for analysis. The first blend was Novec 649 1 part and 9 parts of R1234ZEE. The second one was equal parts of Novec and 1234ZEZ. The third one was 1 part Novec and 1 part ZEZ refrigerant. And the last one was 9 parts Novec and one part R1234YF refrigerant. So the schematics of the cycle look the same pretty much as in case of a traditional zeotropic cycle. The diagram of the cycle in pressure and enthalpy coordinates also is similar, and in temperature and entropy coordinates, the temperature glide of the refrigerant can be seen. And these are the cycle parameters assumed for the analysis. So the motive vapor temperature was set as at 60, 75, and 90 degrees, with 10 degrees superheating in all cases. The condenser outlet temperature was 30 degrees with no subcooling. Condenser inlet temperature was 35 degrees. And 2 evaporator outlet temperatures were analyzed. That's 0 and 6 degrees. There was no superheating in the evaporator. And isentropic expansion and compression in the ejector was assumed with overall ejector efficiency of 0.7. So at first, the parameters in the points of the cycle were found using the assumed input parameters I've mentioned before. The entrainment ratio was calculated using Formula 9, where K is the overall ejector efficiency of 0.7. And then the compression ratio, COP, that's number 10 and 11 equations. And at the end, formulas 12 and 13 are the power of the compressor in the equivalent vapor compression cycle, and the relative difference between this compressor power and pump power in the zeotropic cycle. And as for the results, the entrainment these are the results for the evaporation temperature of 6 degrees. So the entrainment ratio increases with increase of heat source temperature and varies between 0.08 up to 0.49. And entrainment ratio decreases with increase in temperature glide and is lowest for the blend number 4, which has the highest glide of all analyzed mixtures. The compression ratio is the highest also for the blend number 4. And the higher the temperature glide is, the higher the compression ratio is. COP for COP varies from 0.07 to 0.18 for the motive temperature of 60 degrees and is in the range of 0.23 to 0.36 for 19 degrees heat source. And COP drops with increase of temperature glide. And the relative difference in the zeotropic cycle pump and equivalent compressor power, that's the descending lines in this chart, varies from 81% to 97%. And that means that the pump in the zeotropic cycle consumes significantly less power than the compressor working within the same temperature range and the same cooling capacity. In this chart, temperature glide in the vapor generator and drop in heating water temperature can be seen because water was assumed as a heat source fluid. And the drop of the water temperature varied significantly as these blends have the temperature glide of these blends strongly differ. And the heating water temperature drop is the highest for the blend number 4, which has the highest highest temperature glide. And yes, and the results presented in this chart are the same for both analyzed evaporation temperatures. And here we have entrainment ratio and compression ratio for the evaporation at 0 degrees. And general trends and order of the mixtures in the chart are the same as in case of higher evaporation temperature, but the entrainment ratio and COP is slightly lower, and the compression ratio is slightly higher, and the difference between zeotropic cycle pump and compressor power is very similar to the case of the higher evaporation temperature. And in conclusion, the zeotropic cycle achieves significantly higher drops in heating fluid temperature than the conventional ejector cycle. And that means that the zeotropic ejector cycle utilizes the heat source more efficiently. COP of the zeotropic cycle is lower than in case of a conventional ejector cycle. And increase in the working fluid temperature glide decreases COP, and the zeotropic cycle pump consumes up to 96% less power than the equivalent compressor in these analyzed cases. And that's all. Thank you.
Thank you very much. Thank you for a nice presentation. So I see that we don't have any question in the Slido system, probably.
No, we don't. We don't have. No, we don't have. I don't see any
questions. So the situation is the same. So the presentation was made by the same research group, so that we will not be asking the question to ourselves. And because of that, maybe the next and the last presentation, last but not least, also from the research group from Białystok University of Technology, Andrzej Pawluczuk, Kamil Śmieciew, Jerzy Gagan, Dariusz Butrymowicz. So Andrzej, could you just prepare your presentation? So it will be, it should be started exactly at 3:45. Hello? You should be here. Okay. We cannot hear you, Andrzej. Hello.
And now?
Yeah.
You hear me? Okay.
Could you just load your presentation?
Widać?
You could share screen.
Moment. I know, but I presented. I don't know. Okay. What? Oh, it's working.
Yes,
Okay.
it's fine.
Okay. Good morning. The subject of my presentation is experimental investigation of fully passive heat-driven two-phase injector. My name is Andrzej Pawluczuk, and I am a PhD student at the Białystok University of Technology. Today's presentation consists of the following points: introduction, experimental stand, experimental research results, mathematical model versus experiment, and conclusion. On this slide, we can see two types of ejection refrigeration system. The first is basic ejection refrigeration system with a mechanical pump. But the second system does not have a traditional mechanical pump. It is equipped with a two-phase injector. So mechanical liquid pump is the only element of the ejection refrigeration system that consume electrical power. Without consumption of electric power to drive the system will be fully thermal driven. In this slide, I present a vapor liquid injector in section. The multi-vapor nozzle, liquid nozzle, mixing chamber, diffuser. Between mixing chamber and diffuser, we have a condensation wave. In each of these sections, we have a corresponding pressure change. In vapor nozzle, we have a drop of drive pressure to condensation pressure. Next, we have mixing pressure with slightly lower than condensation pressure. After that, we have a very high pressure increase along with the shock wave. And finally, a slight increase pressure in the diffuser. Now we have experimental stand. In this picture, we see experimental stand for testing two-phase injectors. The components of the stand are injector, a steam generator, a condenser, fan cooler, circulation pumps, electrical heater, accumulation tank with a coil, and some of temperature sensors, pressure sensor and flow meters. That's look like the experimental stand in our laboratory. and this is a measuring system used to data acquisition. The injector is a small device. Its length is less than 20 centimeter. There is a 3D model and photo of our injector. Experimental research results. This is a description of the two-phase injector measuring system. 5 series was selected for this presentation. It should be emphasized that the presented results of experimental research were carried out for an injector pump in passive conditions. In other words, it's a fully heat-driven device. On this slide, we have a relation of pressure ratio in function of heating of the liquid phase. When heating of the liquid phase increase, then pressure ratio increase. For variable mass entrainment ratio and constant motive pressure, we can observe when the mass entrainment ratio increases, then decreases our pressure ratio, but the efficiency increase. On this graph, we can see injector efficiency in relationship with mass entrainment ratio. So when the heating of the liquid phase increased, then injector efficiency was decreasing. And mathematical model versus experiment. The experimental results were compared with theoretical predictions based on the model proposed by Śmierciew et al. The criteria numbers adopted during the validation of the model are pressure ratio and mass entrainment ratio. The pressure ratio is defined as the ratio of outlet pressure from the injector to the liquid phase pressure at the suction nozzle, and mass entrainment ratio is a ratio of liquid mass flow rate to vapor mass flow rate. Another criteria number is the total efficiency of the injector. He is defined as a ratio of sum of power consumption for isochoric compression of liquid phase and heat delivered to the liquid phase to motive power consumption, defined as a thermal capacity of the vapor generator. The operation parameters to validation of the device was saturating temperature, superheat temperature, pressure in the generator, temperature, condensation temperature, pressure of the condensation, and the main geometrical parameters of the tested injector are nozzle throw diameter, nozzle outlet diameter, diameter of the mixing chamber, the diameter of the outlet from the diffuser, and the liquid gap diameter. Here we have a relationship between the pressure ratio and function of mass entrainment ratio, and we have on the second graph a relationship with injector efficiency and mass entrainment ratio. Like can we see when we have increase of mass entrainment ratio, the pressure ratio decreases, but efficiency increase. And here we have a relationship between pressure ratio and injector efficiency. So when injector efficiency is increasing, then pressure ratio decrease. The maximum error of calculation is less than 2%. And conclusion, it was demonstrated operation of the injector during passive operation under natural operating conditions. The presented results were applied for validation of the previously provided theoretical model with reasonable good agreement between experimental data and theoretical prediction. The total efficiency of the injector is as sufficient for application of the thermal driving cycles, including the ejector cycles, as a liquid pumping device. Thank you for your attention.
Thank you very much.
Thank you, Andrew, for the presentation.
So, Kamil, also as a second chairman person, do we have any question to?
I don't see it. I don't have any question on Slido.
Mm-hmm. And so, again, just because we are the same research group, we will not be asking ourselves for these presentations. Okay, so the only issue which we could have, we could just take you very much for your presentation, for precise. These presentations have been very prepared so that you have managed to present your material, your research material precisely on time. And so thank you very much. So this is the end of this section of this session, and you may just go to another session where maybe there are also another papers presented, and we have the ceremony of closing of the conference, which is planned at 5 p.m. I guess.
Yes, it is 5 p.m.
So we have 1 hour break, coffee break, something like that. But online conference is online. In normal way, we will be discussing a meeting together and discussing what will be the opportunities for the evening, as usual during the conferences. But this time it is just online coffee. Okay, so thank you very much. And this is the end.